Okay, hello and welcome everybody to this Kickstarter Science Colloquium. In fact, the second of this week. This is one of our series of ongoing Kickstarter Colloquium from the work and projects that have been going on over the course of the last year by members of TVS, Stars and Milky Way and Solar System Science Collaborations. Today, I'm delighted to introduce Laura Venuti and Sabina Ustamujic. Apologize for my pronunciation there. And they are going to talk to us about young stellar object and what Rubin is going to tell us about these fascinating types of stars. But it's going to be a novel approach by a joint talk, combining how they are going to make this subject more inclusive and more accessible to a wider range of people. As always, I will ask everybody who is not actively speaking to kindly make sure that your microphone is muted. And if you prefer your camera not to be recorded, please turn it off during the talk. You're welcome to post questions at any time using the chat screen feature of Zoom. And with that, I will hand over to our speaker, Laura and Sabina.
Hi everyone. Can you see me?
Yes, we see your slides.
Okay. Thank you very much. Thank you, Rachel, for the introduction, and thank you everyone for tuning in. So I'm Laura Venuti. I'm a research scientist at the SETI Institute in California, and I am a co-PI of the Kickstarter project entitled Young Stellar Objects and Their Variability with Rubin LSST, combining observations and 3D models for a more inclusive science. So I would like to acknowledge Sara Bonito from the Astronomical Observatory of Palermo in Italy, who's the PI of the project, and Sabina, who's also from Palermo, who's the lead postdoctoral researcher on the project, and will talk right after me. So in this first part of the colloquium, I will present the scientific background and the motivation for our project, and then Sabina will guide you more into the activities that we have been undertaking. So as stated in the title, we are interested in young stellar objects, which are young stars typically younger than 10 million years, surrounded and actively interacting and actively exchanging mass and angular momentum with a protoplanetary disk. Because the spatial scales over which the star-disk interaction develops are often too small to be resolved with interferometric or the direct imaging techniques that are used to map the outer disk regions, a most direct approach to study the inner disk dynamics is to trace the different signatures that inner disk processes leave across the wavelength spectrum, from the UV that traces the energetic emission from the accretion shocks at the stellar surface, to the optical that traces stellar activity, to the infrared that traces thermal emission from dust within the disk. These signatures will change with time, following the dynamics of the star-disk system. Therefore, we want to monitor the time changes of these signatures in order to study how young stellar objects evolve in time. As already clear from this introduction, variability is a keyword of our project. And indeed, variability is a prominent and defining feature of young stars. This diagram shown here on the right illustrates the different phenomena that contribute to the variability behaviors observed for young stars, overall timescales starting from hours out to decades. And a key point to notice here is that thanks to its design and duration, Rubin LSST will allow us to probe variability in young stars across all of these timescales with the same instrument. It will therefore allow us to derive a first coherent and self-consistent view of the behavior of young stars across the time domain. But the typical predominant variability that you observe on young stars is that develops over days to weeks timescales, which correspond to the rotational timescales for these objects. And over these timescales, there are several processes that contribute, starting from magnetic activity and rotational modulation by starspots, to star-disk interaction regulated by the process of mass accretion, to the star-disk geometry that determines which features of the inner disk environment cross the line of sight of the star. As I mentioned earlier, reconstructing the emission of these young stellar objects across the wavelength domain provides crucial information in order to disentangle the different physical processes that contribute to the variability observed. You can see why from these plots on the left that compare the spectral energy distributions expected for a young star actively accreting mass from a thick disk and a young, more evolved star where the protoplanetary disk has already disappeared. And you can see substantial differences between these two spectral energy distributions, which we will be able to probe in the filters that will be provided with Rubin LSST. Indeed, the bluer filters that will be available will allow us to trace the flux excess produced by the accretion shocks, whereas the redder filters will allow us to trace the photospheric properties of these young stars, essentially or relatively unaffected by either accretion emission or the disk emission. So when we combine the measurements of the stellar luminosity in all of these filters on color diagrams, we are provided with a powerful tool to separate the young non-accreting stars, which trace their reference photospheric properties, and then the young accreting stars, which show color excess with respect to this photospheric locus. And by measuring this color excess, we are able to determine the amount of mass accretion on the stars. In recent years, we have obtained a very detailed view of the type of variability behaviors that can be expected of young stars, thanks to a few dedicated monitoring campaigns conducted from space, in particular with the Corot and Kepler satellite. And these panels shown here on top, they show a few examples of the wide variety of behaviors that young stellar objects can display. Some stars show very periodic variability, which is best interpreted in terms of rotational modulation by long-lived starspots at the surface of the star. But other stars show very erratic variability behaviors dominated by intense luminosity bursts that trace the dynamics of unstable mass accretion in the innermost disk regions. And yet another category of young stars are the so-called dipping variables, which are dominated by recurring fading events in the light curves, which trace the structure of dust in the inner disk environment, like warps that form at the base of the accretion columns, and that can cross the line of sight of the star when the star disk system is seen in a near adjoint configuration. So this kind of surveys have allowed us to achieve a very detailed atlas of the different time domain behaviors on young stars on weeks to months timescales. But they have been limited in the physical interpretations of these behaviors. On one hand, because there were only a few star forming regions that could be observed from space along the orbits of these satellites. And on the other hand, because these campaigns were often accompanied by very little color information that would allow us to disentangle the contributions by different processes. And these are exactly the two key points where Rubin LSST will allow us to revolutionize our understanding of young stellar objects. Indeed, a key feature of the survey is that it will provide a very deep mapping of the sky, of the southern sky. Therefore, which for young stellar objects in star-forming regions essentially means that we will be able to map the stellar populations of embedded clusters down to the lower end of the mass spectrum. If we take, for instance, the simulated single visit depth that is expected to be reached with Rubin LSST in the G, R, and I wavelengths, and then we combine it with the expected luminosities of young stars predicted by premium sequence theoretical evolutionary models, we can derive an estimate of the maximum distance at which we expect to be able to detect young stars as a function of their mass, their age, and the amount of interstellar extinction. And a striking feature of this diagram is that for the lower mass regime, so around 0.5 solar masses and less, so essentially for the M-type star regime, we will be able to detect these sources, very young sources, down to distances of tens of kiloparsecs, which is significantly farther out compared to the few kiloparsec radius within which most well-characterized studies of star-forming regions have been limited so far. So this implies two things. On one hand, for regions that are closer to the sun, we will be able to push the census of their members down to the lowest masses. And this is crucial for studies of the initial mass function or star formation history of the cluster. But on the other hand, for more massive stars, will be able to be identified to distances that go well beyond this limiting radius. And so therefore, a huge discovery space for new young stellar populations in different environments opens up beyond the distance of tens of kiloparsecs. But in order to exploit this unprecedented view, we need to develop accurate photometric tracers that would allow us to identify young stars in previously unknown regions by conducting blind searches of the Rubin database. As part of the Rubin survey strategy preparation study, our team has focused on the optimal observing strategy that would allow us to map the variability of young stars across all timescales of interest from hours to years. Thanks to its design, the Rubin LSST baseline survey with a wide fast tip approach would naturally provide us with a homogeneous mapping of variability of young stars on timescales of months to years. And what we have found in our simulation is that it is by combining this long-term, intermediate to long-term monitoring mapping with a short period, just 1 week of intense monitoring in the Rubin LSST filters, we'll be able to effectively trace all timescales, all variability on all timescales of interest down to the shortest variability timescales. For instance, the hours timescales that characterize the luminosity bursts that were shown before. And this will allow us to put short-term variability into context for the long-term variability. And if we do this, Rubin LSST will provide us with a distinct advantage over earlier studies conducted with Kepler, because it will allow us to map at the same time the variability on individual bands and on the associated stellar colors. And when we combine these two information, we are able to study the shape of the emission spectrum from the emitting region, and therefore effectively disentangle the contribution from magnetic activity, from the contribution from accretion shocks, and then the contribution of interstellar extinction. This wavelength dependence of the observed variability amplitudes on different time scales is also a critical parameter to provide to inform theoretical models in order to derive an estimate of the physical parameters of the inner disk region. For instance, for stars that are observed at lower inclinations, where the variability we see is dominated by surface features like spots, the information on how the variability amplitude changes with wavelength is essential to derive an estimate of the temperature contrast between the spots and the stellar photosphere, so whether they are hot accretion shocks or cold magnetic spots, and then to derive an estimate of what fraction of the surface of the star is covered by spots. And on the other hand, if you have a dipping variable, obtaining a measurement of the amplitude of the dip as a function of wavelength is essential to compare with models to derive an estimate of the composition of the inner disk structures in terms of grain size and the number of components that can produce the observed light curve. So far, I've focused mostly on short-term variability behaviors, but as I've shown in the diagram at the beginning, young stars are also known to show significant variability on longer timescales. The most dramatic of such long-term variability events are the so-called outbursting behaviors, such as the ones that are displayed by XOR-type sources, which are characterized by magnitude increases on the order of a few magnitudes over timescales of months to years. But a more moderate type of variability on the longer term is the one that arises from structural changes in the inner disk that can take place over timescales of a few years or less as a result of the stress between the stellar magnetosphere and the inner disk itself. However, our understanding of long-term variability behavior so far has been anchored to a handful of sources that have been studied in detail. And the lack of systematic data set that allows us to cover all timescales, all intermediate timescales of interest from the short term to the long term, has prevented us from gaining a statistical view of the connection between short-term and long-term variability behaviors in the economy of prime sequencellar evolution. So this is the type of information that we want to achieve from Rubin LSST. And in order to prepare for the Rubin LSST survey exploitation and to prepare for the identification and the analysis of new and young star populations, we have started an exploratory study that relies on all currently available large-scale surveys in filters relevant to Rubin LSST, so essentially G, R, and I, and that cover young star forming regions that are currently that have been previously studied. So our approach consists in selecting a reference sample of young stars, young star forming regions that have been already studied in the literature, possibly from with different methodologies, in order to have a robust reference sample. Compile light curves for each star in these clusters from publicly available datasets like PanStars and ZDF in filters relevant to Rubin LSST, in order to get a long baseline coverage of their variability, albeit with an irregular sampling. And then apply statistical metrics to extract the variability, the typical variability we observe on each young star as a function of timescale that is contained within the light curve. So that would essentially correspond to taking a box of a certain width, which corresponds to the timescale of interest, have this box scan along the light curve, and for each step measure the amplitude of variability contained of the data points contained within the box, and then extract the average information of how these variability amplitudes changes with the width of the box. It is with the timescale. With this approach, we can populate a diagram like the one shown here, which compares the amplitude of variability. So in this case, it's on the mass accretion rate, but more generically, the amplitude of variability measured in the light curve as a function that ties on the timescale considered for the same stars across all of these different timescales. And this approach will allow us to address two key questions. First one is, what is the causal link between small-scale disk processes, such as the one traced on short timescales, the 2x timescales, and large-scale eruptive behaviors, such as the ones observed in XORs over timescales of months to years? And the second key question is, how universal are long-term dramatic variability events in the prime sequence evolution of young stars? So in other words, how common is it for a young star to undergo an XOR phase during their evolution? And the reason behind this question can be understood if you examine this diagram. So this diagram shows, as the sketch that showed at the beginning, that as we move out to longer timescales, larger amplitude variability starts, larger scale variability starts to emerge, as we expect. But if we measure this variability trend with timescale for the same stars, and then we measure at each timescale the typical amount of variability, what we observe is that the amount of variability typically measured across the population on timescales of years is still consistent with the timescale measured with the variability measured on timescales of days to weeks. So unless we get a detailed statistical picture of the time domain behaviors of the same stars on all timescales from hours to years, our answer to these questions cannot be achieved on a statistical level. So to conclude this part of the colloquium, young stars can show distinctive variability traits triggered by a variety of physical processes that take place in the inner disk. And monitoring this variability traces dynamical changes in the star disk system along their evolution. But in order to derive a coherent picture of variability of young stars across the time domain, we need a homogeneous database that would allow us to probe young star populations across a variety of ages and environmental conditions, with sensitivity to the disparity of inner disk processes and consistent precision down to the photometric precision down to the smallest variability amplitudes that you want to measure. And these are the reasons why Rubin LSST will allow us to fill in this piece of the puzzle. Thank you for your attention, and then I will now stop sharing and let Sabina share her talk.
I will take this opportunity to ask, do you prefer to have questions at the end, or we can do them now if you prefer?
That's up to you. Maybe like Sabina wants to give her talk now, we can then
Absolutely
get a more comprehensive view and get all of the pictures at the end, or all of the questions at the end.
Okay, that's fine.
Okay. Can you see my screen?
We can, but you're not in full screen mode.
Okay. Is it okay now?
That's great.
Okay. So, hi everybody, I'm Sabina Ustamujic from INAF Osservatorio Astronomico di Palermo. And as Laura already gave a nice context about our project, I will talk more about the work I have been doing, collaborating very closely with, especially with Sara Bonito and Laura Venuti. And of course, there are also other collaborators that we have. Here you can see a picture of the workshop we did in June in Palermo to talk about this work and organize. And I would like to mention, as I'm going to talk about the 3D models, I'm going to mention especially Salvatore Orlando, which has been doing a lot of work with us with the 3D models. Oops. Okay. Do you see the next? Have you seen the second slide?
Yes, we do.
Okay, because I had some problems to change. Okay. So as Laura already explained to all of us, young stellar objects show a very variable behavior, which we can observe variability in very different time scales and with different origins, which mainly are related with the dynamical processes that happen in young stars. The aim of our project is to investigate the variability in young stellar objects at different time scales. And for this purpose, we are focusing mainly in two activities. The first one is analyzing the light curves from public data sets, like, for example, Pan-STARRS and Gaia, selecting young star forming regions from available large-scale surveys in preparation for Rubin LSST data. As Laura already mentioned, the exploratory approach that we are taking in preparation for Rubin data is to select different time variability in different time scales to study, from short term, like that can be from hours, days, to long term in months, years. And we have selected the homogeneous data for different stellar populations, and we are studying all together to try to derive a consistent picture that might give insights on the variety of physical processes across the time domain. I would like to focus mainly on our second activity, as Laura already talked about the first part, which is we are working on developing models and 3D renderings, reproducing the geometry of stardust systems that could explain the variability that it's observed in the data, and that will give rise to specific light curve patterns. So our purpose is to identify the origin of the variability observed in light curves and create models that can represent correctly that variability. I would like to first talk a little bit about data visualization, which of course, here, like all of us, we all have different scientific interests, but I feel confident to say that all of us are interested in data visualization because it's fundamental to represent our study. And I think that it's a quite challenging task to do it properly because we need to put together scientific, artistic, and technical skills. And of course, when it's done in the proper way, it can be very useful to describe the phenomena and physical processes that we are studying. There are different types of representations that we can do that mainly should depend on the purpose and the target that we have. And I would like to illustrate this with an example. Here, for example, you can see an accretion disk of a young stellar object, where you can see this is the output from a numerical model, and you can see the disk, the central star, and the magnetic field configuration. And I would like to show how we can represent this same model in different ways, depending on the purpose and the target we have. For example, one representation could be to a scientific representation, where mainly we aim to represent accurately a physical phenomena. Here, for example, you can see the disk with the star, which is connected with accretion funnels, where we illustrate how the material from the disk is transported to the star, and in this process are created these flares that you observe, which emit in ultraviolet and X-rays. This type of representations is very useful for specialized scientists, which already have some kind of knowledge about the phenomena we want to present. A second type of representation could be an artistic representation, which this same phenomena we are seeing a completely different representation, which mainly we represent as an essential fact in putting the focus in the way that we represent the fact that that it has to be very appealing, because in this case the purpose is to capture the attention. And it's more, the target here will be more the general public, for example, for dissemination events, for which in general don't have a good knowledge about the phenomenon we are representing. The third representation could be this one, which is a schematic representation of what is a protoplanetary disks, where we represent all the parts, where the accretion streams, the disk, and we also describe in a schematic way the chemical content of a protoplanetary disk, and we indicate also the temperatures. This can be very useful for students, for example, for educational purposes. And the fourth representation I would like to show you, it's a 3D printable object representing an accretion disk. This kind of representation is a simplified 3D printable representation, which the way we visualize this representation is by printing and touching the object, which can be very useful for visually impaired community. And here is the focus of our project about inclusiveness in science. Being aware of the importance of data representation in Palermo, so a couple of years ago, we started the project 3D Map VR, which stands for 3D modeling of astrophysical phenomena in virtual reality. In this project, we combine accurate 3D magnetodynamical simulations performed with parallel numerical codes for astrophysical plasmas with data analysis and visualization applications. We combine these two things to create public galleries of scientific models. The galleries we created have been already published in Sketchfab platform, which is a free platform where the models can be explored using a simple browser, or of course we can use all the power of the visualization in virtual reality if we have the proper devices. The products that are already available are the 3 points I'm presenting here, which the first one are for Sketchfab galleries, which you can find in the links I have shown here. So in these galleries, we illustrate scientific models of astrophysical objects. Here you can show how some of the models are explored, which is very interesting because we can explore interactively all the models and interact with the model and see from inside all the phenomena. The first gallery, which is called Universe in Hands, represent accurately astrophysical phenomena derived from numerical models. In the second one, which is called the Art of Astrophysical Phenomena, we make artistic representations of different astrophysical phenomena. But of course, we always take into account the physical knowledge we have about that phenomenon and try to represent it accurately. The third one, the science of science fiction, represents mainly astrophysical phenomena which have been represented in very popular science fiction movies. And then the fourth one, which is anatomy of astrophysical objects, we present different models which are very useful for educational purposes, as the one I have shown before about the protoplanetary disk. We also have done web series in Italian and English, which can be viewed in our YouTube channel, which mainly represent the astrophysical objects that are presented in the galleries, but with an explanation where we present all the phenomenology around. And the third one is a publicly available app called Star Blast for virtual reality that we developed, where can be used in virtual reality to explore different supernova remnants, and also it can be downloaded also completely free. From the models we developed, we also can make 3D printable models. Here I show a couple of examples that have already been printed in 3D. On the left, you can see a jet of a young stellar object and a disk which is available in Sketchfab, but has also been adapted by NASA 3D resources. And there are you can find in the link the models which can be downloaded and to be printed. The model on the right, which is also a numerical model, it's a supernova remanent IC443. We developed the numerical model, and it has been also adapted to be printed in 3D. It's also available in between the NASA 3D resources, and we have already at home different models that you can see that has been printed. These are other models, but we have also the model of the IC443, which is available to be separately printed, where you can print the ejecta that you see here from the star, for example, which is colored. Separately printed, you can have the molecular clad, which is shown in purple, and so it's quite instructive to have this model also printed. And of course, it can be very useful for visually impaired scientists. In the context of our work in Transient Variable Stars group, we are trying to collaborate to make a more inclusive environment to present Rubin science. And we are developing a catalog of publicly available interactive 3D graphics and 3D printed kits to adequately present Rubin science to visually impaired researchers and members of the community in general. So here I show a couple of examples of models that we already developed. On the right, you can see a warped disk, which has been deformed in the internal part to represent what would look like a warped disk, a warped accretion disk. And on the left, you can see a very simple model, which represents a star with a spot that has been represented with a different texture, which can be also touched. These models are not available for the moment, but we are planning to put them available. We are doing the models are ready. We are doing some tests, as we don't have a 3D printer at home. We have some collaborators in USA that can do some tests for us, and we are planning a visit for the beginning of the next year to do some printing tests, and then of course we are planning to make available all these models and to continue completing the catalog. I would like also to mention that thanks to the work we have been doing, we met other people inside the Transient Variable Star Science collaboration, which is also interested in our topics. And recently, it has been some months ago, it has been created a data visualization and representation group, which I'm the co-chair together with Sally McFarlane from South African Astronomical Observatory. And we are interested in the different topics. Of course, here I have been talking more about our work in virtual reality and 3D printed models, but we also have people interested in digital domes, which is mainly the work that Sally has been doing. Also, other people that is doing data sonification. So, of course, if you are interested in these topics, I encourage you to contact and join us. And that's all from my part. Thank you for your attention. And if you have any question, let me know.
Thank you both, Laura and Sabina, for two fantastic aspects to this work. And that's really amazing work that you have, especially in the visualization of these really complex objects. So if anyone has any questions, please feel free to put them in the chat. I'm going to take the chair's prerogative and actually ask about some of the 3D visualizations and the printing tools that you do. What kind of hardware do you need to actually use that?
Well, mainly, of course, if you want to develop the models, you need a computer with good graphics, but it depends on the resolution of the model. I think that the most difficult part is for the visualization, because of course you can visualize the model using a browser, but the complete immersion that you can find with virtual reality devices, it's the best. So the best will be to have virtual reality devices as Oculus, for example.
Do they use a common standard? I have a Quest 2, for example. Would that work?
Yes. Actually, it should work. We have the old ones, the Oculus one, but actually we are also buying a Quest 2, so it should arrive also. Then I think that the next month. So
nice.
we will try also, but it should work with all the devices, and it's quite simple to use in this Sketchfab, because when you connect to Sketchfab, you can you visualize the model on the browser, and then you have an option to start the virtual reality, and you automatically can see it with your device. And of course, if you want to have the possibility of doing the 3D printing, you need a 3D printer, which actually is the problem for us at the moment. But it's always easier, because the fast development of 3D printing has lowered the prices. So actually, 2 years ago, it was they were very, very expensive, and now it's much easier to find 3D printers. So yes, that's mainly the. I hope I have answered to your question.
Yes, absolutely. And we should talk, because LCO has a 3D printing facility for our engineering side. So collaboration is possible. There's several of them in the US now. So
yeah, that will be great also, because actually for that part, we have also in the project Nino Cucchiara from USA, and they also have I think 2 or 3 3D printers. And so actually we already talked with them, and I should be doing a visit.
Oh, good.
Probably in January or February, and we are planning some tests together.
Good, excellent. Are the models difficult to develop? I mean, I can imagine other science topics in TVS being interested in developing models for their own science. So is it difficult to expand this? I'm wondering if it's worth having a workshop so that you can show us all how to do it.
It's I mean, it also depends on the origin of the models. It's a very long process when you develop a numerical model from scratch, for example, which it's not only for visualization purposes, but it's also for scientific purposes, where you can derive a lot of information from that. It's much, of course, we use the numerical simulations to represent our models when they are available. In some cases, when we don't have numerical models representing the phenomena, what we do is try to create the artistic impressions of the phenomena, which of course have to represent accurately the knowledge we have about the phenomenon we are trying to represent. But it's much faster, because we do not need to develop a numerical model. We just need to have clear the kind of representation we want to do, and try to create our model depending on the target also we have, and that can be much faster. We usually use a lot ParaView for that, or Blender, for example, which can do a lot of things.
So can you take output from Blender directly? And
I have been using mainly Blender for yes, with Blender, for example, you can do some kind of modifications also for the model. For example, the model of the disk, I started with a numerical model, which we already had from an accretion disk, and I imported that model in Blender in order to create a new model of warped disks. So in Blender, you, for example, can modify the mesh you have, for example, and you can create deformations and you can do a lot of stuff. I'm not an expert because actually I started to use Blender this year, but it has a lot of possibilities because before that I have been using mainly ParaView, which is more it's very useful for scientific analysis of data
Right,
flows.
Right. But Blender's a free tool that is extremely powerful, so I can see its potential there.
No. Yeah, ParaView is also free. So
good to know.
Yes, but Blender, it has so much possibilities. So this is why I say that I have been using like I think that 5% of the tools of Blender. So I know that there is so much to discover there. So yeah.
Thank you. I see a comment from Tomislav. Did you want to repeat that verbally?
Oh, I just wanted to say that the 3D printers are really becoming quite cheap. So, for example, I bought one for around 400 euros. It's a small one. It's only 10 centimeters, the size of the prints, but still you can get it for not too much money.
They've definitely become more
from curiosity, is it a resin printer?
Yes. It's. I mean, I'm not an expert in this kind of printers. It's some kind of resin. It's not, of course, the top one. It's. I mean, it's not the quality of this resin is not very high with the printers that cost a few thousand euros, but it's quite strong, the print itself. So
yes, I asked because especially the resin printers are much more affordable now, especially when you don't need to do big stuff, when you only need small models until like 10 centimeters, as you told. They are quite affordable.
Yeah, that's right. It's only 10 centimeters. I think it's resin, the material, so it's not some kind of thread and so on. So it can be purchased for a few hundred euros at the moment.
I have a question for Laura, if I may. I was interested that you mentioned the young stellar objects radiance in the UV and X-ray, and of course those are elements that Rubin itself won't provide. So can you comment a little bit about the other complementary observations you might need in those wavebands in order to identify young stellar objects in Rubin?
So in order for the identification itself, the most powerful tracer that Rubin will provide is the variability, because all of these young stars are expected to exhibit a very distinctive levels of variability, which are different from accreting stars, non-accreting stars, and different from field stars. So the studies that we've conducted so far show that if you have sufficient precision, all young stars exhibit some level of variability above the field level.
Okay.
Then, of course, to study, to drive a detailed picture of the inner disk structure, we are planning to conduct, for instance, auxiliary spectroscopic observations using several facilities that are available, will become available. And these allow us, for instance, observations in the H-alpha or these line emission bands, which trace the dynamics of the accelerated gas that flows from the inner disk to the star. So this kind of information is critical to allow us to reconstruct the structure, the more extended structure around the star. And so our team is involved in several of these spectroscopic surveys and spectroscopic survey facilities that have already been used for similar studies on limited populations and are also being developed to conduct more extensive surveys that will take place on the same time frame as Rubin. Yeah.
Great, highly complementary.
Yeah.
Excellent. Well, if there are any other questions, that jump in now. And if not, I would like to thank Laura and Sabina again very much for two fascinating talks. That was really excellent. And just a reminder that we have the third of this week's Kickstarter Colloquia taking place tomorrow at the same time. So I look forward to seeing everybody then. Thank you, Laura and Sabina.
Thank you. Thank you.
Thank you, Rachel.
Thanks, everybody. Bye-bye.
Bye.
Bye.